All right, doing okay so far? All right, so in this shaded region, if you were to draw in little rectangles, okay, notice how those rectangles do not touch the axis of symmetry. So this is a washer example. So let's go ahead and write our washer setup. Volume equals, maybe you want to initially pull that pi out front. If you want to do that, that's fine. So if it's a washer, we have to figure out the outer portion, what that radius would be, and then we have to subtract the inner portion, what that individual radius would be. Since we're revolving it around the x-axis, this will be a dx integral. We want to take a stab at either of the radii or maybe the bounds. What do you think, Caitlin?
The bound 0 to 1.
0 to, okay, so definitely 0, but the area stops right there. Oh, the y, yes, the y-axis. If this was a dy problem, it would be 0 to 1. Yep.
So
Okay.
0 to pi?
Maybe we got to figure out what that intersection point is. Okay, so you might have to use your graphing capabilities, or maybe you know where they cross each other. Yeah. It is pi over 4. Okay, so you could write pi over 4, or you can use the decimal representation. I think it's 0.785, something like that. Right? If you think about the unit circle, where is sine and cosine exactly the same? That's at the 45-degree mark. Okay, square root of 2 over 2, comma square root of 2 over 2, aka pi over 4. All right. So if this is our little region here, and revolving it around the x-axis, the outer radius is coming from the blue graph. Okay, that's kind of our donut curve. And then the inner radius is coming from the red graph. That's like our filling, where it starts. Okay, so we need the outer minus the inner. That way we get that specific location we are trying to find the volume for. So the outer equation we said was cosine. And if we subtract the axis that we are rotating it around, just like we did yesterday, it would be minus 0, but you don't have to write that if you don't have to, or if you don't want to. The inner radius is the sine graph minus the axis of rotation. Again, it's 0, so you don't have to write it if you don't want to. And go ahead and let the calculator do the work from there. Now you do have to be careful with this one. Since we're working with trig, you have to make sure you're in radian mode, right? Working out for us? Should I take the silence as a yes? Yeah? Okay. All right, let's check out some more on the back. Find the volume of the solid formed when the region enclosed by these graphs is rotated about the following axes. All right, so we have, it's basically the same type of graph and equations, we're just choosing a different way of rotating it. So let's perhaps draw our pictures. So our first equation is y equals x, linear function going through the origin. Our second function is quadratic, so starts at the origin and curves upward like a U. The region bounded by those graphs, we have all of this inside. And in part A, we're going to rotate it about the x-axis. So again, if you were to draw in your little rectangles, your Riemann sum rectangles, they would not touch the axis of rotation. So we got a washer. So let's go ahead and set up our volume. Volume equals pi. We need the outer radius minus the inner radius, x-axis rotation, so a dx integral. Any takers on radii or bounds? Good, Eric?
Bounds are 0 to 1.
0 to 1. Alright, so 0 definitely at the origin, and then figuring out that intersection point where the two of them are the same. That would be at 1, 1. On both the x and the y. Alright, outer radius, inner radius. Donut versus filling. Good, Caitlin?
Is the outer just the x?
Yep.
And then the other one
Is the x squared. Perfect.
is the x squared.
Mm-hmm. Yeah, you don't have to write the zeros in there if you don't want to. Alright, you could probably do this one by hand, but for space purposes and maybe time purposes, if you want to use your calculator, that's okay too. Notice how this would just be x squared minus x to the fourth, and you'd have to integrate those. Those are easy for you. Any takers? Good, Caitlin?
0.418.
0.418 or 9, yep, however you want to round. You can truncate it or round it, either one. Check out. Alright, let's try the next one. We're going to have the same graph. This time we are revolving around the y-axis. So if we were to draw our little Riemann sum rectangles in this one, they would actually be going horizontal, pointing towards that axis that we are revolving around. And again, notice how those rectangles don't touch the axis of rotation. So we got another washer. We are revolving it around the y, so this is a dy integral. Takers on the bounds or radii. Go, Caitlin.
The bounds are going to be 0 to 1.
Still 0 to 1, yep. And actually they're probably going to be that way for all of them because that's the beginning and ending intersection points for this curve. So bound 0 to 1 for all of them. Okay. What about the radii? This time the donut's kind of on its side. Outer donut, inner filling. Good, Eric?
It is square root of y minus the x squared. X squared and x squared minus.
There we go. Okay. So we got to be careful with the dy integral. We have to make sure our equations look like x equals. And the first one already looks that way. Okay, x equals y. But for the parabola, you have to take the square root Technically, you should have a plus or minus the square root of y, but since we're dealing in the first quadrant, it would just be the positive version. Not that it matters anyway, because you're going to end up squaring it, which would get rid of the square root. Alright, so go ahead and let the calculator do the work. This would probably be another one you could do by hand, right? This would be y minus y squared. Going backwards from those is easy. Any takers? Good, Eric?
Is it 5 or 6?
Let's see. I have the decimal version on my paper. Yes, pi over 6. Or 0.523, 524, however you want to round. Or truncate. Good. Alright, so those two were kind of basic ones if we're revolving around either the x or the y-axis, but we know sometimes they're not that simple. We might have to start revolving around different axes, sometimes numbers. So let's go ahead and check out these ones. We'll draw our picture. Alright, so this time our axis of rotation is y equals 2, and if we said this intersection point was at the height of 1, then our axis of rotation is actually a little bit above that. So if we were to draw our little Riemann sum rectangles in the direction of the axis of rotation, or perpendicular to the axis of rotation, they would be vertical. So in terms of our integral, we know this is going to be a dx. Okay, a horizontal axis. We already said the bounds would be 0 to 1. So now we just got to figure out outer radius, inner radius. Outer donut, inner filling. Good, Eric?
And 2 minus x squared.
Say it again.
2 minus x squared.
2 minus x squared, okay.
And then 2 minus x squared.
2 minus x. Okay, so that is one way you could do it. If you wanted, typically yesterday, didn't we write like equation minus axis? Remember that? If you had those switched, that's completely okay. Because you're squaring it, it's going to reverse the order and it would still work out. So if you had x squared minus 2, you should still get the same solution. Okay? And then same thing over here. If you had x minus 2, that would still be okay. Okay? So go ahead. This one would be a little bit more tedious to solve by hand because you'd have to do some expanding, combining like terms. You would probably be able to eventually get it, but let's go ahead and we'll let the calculator do the work for us. Any takers? Okay, Caitlin?
1.676.
1.676. Agree? Work out? Alright. Let's go ahead and draw our next one. This time our axis of rotation is x value of -1.
Make it a lot easier, huh?
Drawing little rectangles in the direction of the axis, they would be horizontal. So we have a dy integral. Bounds still 0 to 1. So in relation to this axis that we are revolving, we have to figure out what is the outer function, okay, the donut, and what's the inner function, the filling. Go, Caitlin. Uh-huh.
Y
Yep.
minus, no, plus 1.
Plus 1, right. We subtract the axis, but since the axis is negative, it would change to a plus. Good. So outer function minus the axis, and then we would need the inner function, which is just that y minus the same axis. Again, you could probably do this one by hand. You'd have to do a little bit of distribution, combining like terms, but go ahead and let the calculator do the work. What do you think? 1.570?
Yeah.
1? Can we round it up to 1? Yeah, you can? Okay. 0, 1, either one. Okay. more brain power. Checking out? Alright, I want you guys to try the last two. Bless you. Brave Soul for the first one. What were your radii? Donut minus filling. Go, Caitlin.
X plus 4,
Uh-huh.
and then x squared plus 4.
X squared plus 4. Those look good so far? Okay, remember they could be switched. That's okay too. And calculator volume, what do we get?
4.608.
4.608. We agree? I do too. All right. What about the last one? Radii? Donut minus filling. Go ahead, Cameron. Alright, so y minus 17 and the square root of y minus 17. Again, those could be switched. Check out. Alright, so then volume, go ahead, Cameron. 278, 9. Okay, somewhere around there. Check out. Perfect. We feeling okay with washers? We still good with discs from yesterday? Do we see the difference between the two? I think the donut example helps, right? It's also yummy. Okay. So what I want to do, we're going to stop there for today, because if you look at the next page, we're going to get into some kind of crazy integrals or volumes to find. We're going to be doing a Play-Doh activity the next few days, okay, to make sense of this. So I think that's going to be fun in addition to the donuts we had today, okay? But if you go ahead and look at page 15, okay, that's where your homework kind of starts. With what we've covered so far, you should definitely be able to do 19 through 30 based off of the graph they give you. And you could actually probably do some of the multiple choice ones. If you come across a question that says anything that says cross sections, like if you take a look at number 1 here, you see how it says cross sections of S perpendicular? Okay, we haven't discussed that yet. That's kind of the Play-Doh activity we're going to do. So if it ever says cross section, you can skip that one if you want to tackle some of the homework problems. Okay? So we still have quite a bit of time left, maybe close to 15 minutes if you want to get started on some of those. But other than that, you can use the period wisely, okay?